Okay, hello everyone. Welcome to our hybrid physics colloquium. It's so great to see so many of you here in person. I know at least some of you showed up in person just for the coffee and cookies, but that's okay. So our first colloquium of the year is about dark matter meets condensed matter. And for those of you who go down into the basement, once you get off the elevators, if you turn left, there's a sign for condensed matter, and we tacked up another little part to the sign. So it now says condensed and dark matter labs this way. So we are very fortunate to have with us today Yonatan, or Yoni for short, Kahn, who is an expert in essentially developing new techniques and new technologies to build dark matter detectors based on a lot of fascinating stuff that condensed matter people have been doing for a while now. So we have gotten the condensed matter people to join the dark side. And soon we will get everyone else to join the dark side as well. And we will take over the entire galaxy and crush the rebels. We will discover what another 25% of the universe is made out of. If you have any questions during this colloquium, Yoni has said that he would be happy to take them live. If you're in the room, please just put up your hand and I will come running over to you with the mic. Or you can type into the chat and Q&A if you are online. All right, without further ado, I will now turn it over to Yoni.
Thanks, Miriam, for that really kind and wonderful introduction. It's a pleasure to be giving this colloquium. I have actually been to University of Toronto once a couple of years ago. I'd love to come back in person sometime, when COVID and the whole situation permits. But it's really nice that this hybrid format allows me to be able to talk to you about this really fascinating subject today. I'm just going to start off with a little bit of a review of how we know that dark matter exists. So many of you have probably heard talks that start with dark matter and rotation curves and things like that. I think those are great historical motivations, but really we have amazing quantitative evidence for dark matter right now, and I just want to review that story for you. So about 380,000 years after the Big Bang, the universe took a selfie. And I mean that quite literally. We have photons that are a snapshot of the state of the universe from that amount of time after the Big Bang that come to us today and are known as the cosmic microwave background. So this is a map of hot spots and cold spots on the sky. And if you take that map and you Fourier transform it, that gives you these characteristic peaks and valleys that tell you about a certain kind of angular size of these hot and cold spot blobs. And fitting that curve so well that you can barely even see the error bars, that the scale and the residuals is just tiny out here, tells you that there is something that's gravitating that doesn't carry electric charge. So that's cosmologically what we mean by dark matter. And we can measure the amount of that stuff in the universe to 3 significant digits, which is just amazing. So you really cannot fit this curve without some component of the universe that acts like dark matter. So of course, there's a whole panoply of other pieces of evidence for dark matter that come from astrophysics and cosmology, but I think this one really is very hard to build alternative models for things that can explain things like rotation curves that can also explain this if it's not dark matter. Okay, so we have a lot of open questions about dark matter. We don't know how much it weighs. We don't know if it has any non-gravitational interactions, and we don't know how it was made in the early universe. So the way that we proceed is we postulate some answers to these questions in order to make some progress. So maybe there's some sort of interaction between dark matter and some new force that can annihilate dark matter into standard model particles. And then we can ask the question, based on those models, how can we detect dark matter that is floating around in our galaxy on Earth? Because that's really the missing piece of the puzzle. We know it exists cosmologically, but we've never seen a dark matter particle on Earth. So what I do is use tools from high energy physics, plus, as Miriam mentioned, condensed matter, atomic physics, material science, quantum information, any other branch of physical sciences that I can get my hands on to understand dark matter interactions in detectors on Earth. And I find this to be a really fascinating and interdisciplinary area to work on. I learn lots of new stuff every day, and so do all the people in my group. And I think it's a ton of fun. So let's review what dark matter is doing, kind of zooming in from the universe as a whole to just our galaxy. So this on the left is a snapshot of the dark matter halo of a simulated galaxy. So there's amazing simulations that simulate the gravitational interactions of many, many, many particles. Kind of these blobs here represent the density of stuff. So you see there's a big cloud of dark matter and then these kind of dense subhalos. So our galaxy actually sits barely visible in the center. Most of the size of our galaxy and also the mass is made up of dark matter. But if we kind of zoom in and look edge on at a galaxy kind of like ours, we live about 8 kiloparsecs away from the center of the galaxy. And we can understand what dark matter is doing near us by doing local measurements of stars and using classical mechanics. So one thing we can apply is the virial theorem that tells you the average kinetic energy of a test particle is equal to its average potential energy, which is coming from the amount of stuff inside a given radius, capital R. And that tells you that the velocity of dark matter near us is about 10 to the minus 3 times the speed of light, or about 300 kilometers a second. This is a typical speed that has to do with the speed that the sun is rotating around the center of the galaxy, also within a factor of a few of the galactic escape velocity. But you'll notice the mass canceled out because the equivalence between gravitational and inertial mass. We don't learn anything about the dark matter mass from this measurement. Likewise, by measuring the motion of stars kind of into and out of the plane of the galactic disk, we can measure the local dark matter mass density, which is about a third of a proton's worth per cubic centimeter. Again, this is just a product of the dark matter particle mass and its number density. So once again, this doesn't tell us the mass. It's either a few heavy particles or lots of light particles. So if we ask what possible masses could dark matter have, the answer is kind of scarily large. There's at least 50 orders of magnitude if you think of dark matter as a fundamental particle, where the very, very lightest possible dark matter is such that its de Broglie wavelength, its quantum wavelength, is the size of the smallest dwarf galaxies that we've seen. If dark matter were any lighter, it would be quantumly fuzzed out and wouldn't be gravitationally bound in a meaningful sense. Then the heaviest elementary particle that we can talk about is the Planck scale. And you can even, if you want, continue this line 50 orders of magnitude to the right, and dark matter could be something like a primordial black hole that's a big, giant composite object. So there are a lot of places to look on this plot, and much of my talk will be devoted to understanding how we can do experiments to cover all of our bases for dark matter over as much of this giant parameter space as possible. Okay, so the traditional model of dark matter that goes all the way back to this amazing paper from Edward Witten, whose name you might recognize from string theory, but this was really a phenomenological paper back from 1985, an idea for how to detect weakly interacting massive particles or WIMPs. So if dark matter comes in and smacks a nucleus, so it's non-relativistic, which means you can do everything using non-relativistic quantum mechanics or even classical mechanics if you can make your life easy. It deposits a momentum Q on a nucleus that goes and recoils, and that thing now carries some kinetic energy that you can try to see in some detector. And the kinematics tell you that whether, depending on whether dark matter is about the same mass or much heavier than the nucleus, how efficient you are at transferring that energy and momentum to the nucleus. So if the masses are comparable, you should think of this like a billiard ball collision, where you can stop the dark matter and have the nucleus take all of the kinetic energy away. Whereas if the dark matter is much heavier, it comes barreling along like a bowling ball into a bunch of bowling pins, kind of knocks a bunch of nuclei out of the way. And you can't transfer all the kinetic energy, but the nucleus is going to come out with high enough energy that you can see it do something in your detector. Maybe ionize some other atoms or make some scintillation light. So the strategy, which is basically implementing this program, which was proposed 3 decades ago, is fill a giant tank with some stuff, for example, liquid xenon, bury it under a mountain or deep underground in a mine shaft, and you look for the recoil energy deposited by dark matter from this scattered nucleus. So that program has been amazingly successful. So all of these kind of Nike swooshes on this plot represent different experiments. Some of them are made of noble liquid. Some of them are solid state detectors of the kind that Miriam works on. Some of them are things like scintillating bubble chambers. But all of them have this characteristic shape where there's some cutoff at low dark matter masses, which is the x-axis, where the detector threshold is. So you can't see any nuclear recoil below that. Dark matter that's too light isn't efficient enough at depositing kinetic energy on the nucleus, and you can't see it. And then the curves kind of go up to the right linearly because the dark matter always has enough kinetic energy to do something, but the number density goes down as the mass goes up. So there's fewer dark matter particles, so your rate goes down. And the amazing thing is that especially these liquid noble detectors have achieved zero background with many tons of material, which is just an amazing technical achievement. We would have liked to say, we've discovered dark matter with one of these detectors, but really they've seen literally nothing. So all null results so far, and so all these gray regions are actually exclusion limits. Dark matter cannot exist with a mass on the x-axis and a cross section with nuclei on the y-axis above inside this gray region. And so the projections for future experiments are kind of going down here. Eventually, we're going to run into backgrounds from neutrinos, so we'll be able to see something, but we won't necessarily be able to disentangle it from dark matter. Okay, so what I want to focus on in my talk is this white space to the left. So there's really this unexplored frontier where we can turn around that kind of penalty you get from the mass density by saying if dark matter is very light, its number density goes up. So if you have a detector whose threshold is low enough to see a small energy deposit from the small kinetic energy of low mass dark matter, the rate could be very large, and you might only need 10 grams of material rather than 10 tons in order to make a discovery. So really the prototype experiments that live in this low dark matter mass parameter space really start out as tabletop experiments, which you then go and put underground if you want to go to the lowest background environment you can get your hands on. Okay, so one useful perspective in the connection between dark matter and condensed matter physics here is, can you think of your detector like a bag of free particles? So as I've been working in this field, I've learned particle physicists like thinking of things as fundamental particles where there's just nothing else around. Your ground state is the vacuum. You put a particle here, you put a particle here, you collide them, and it's just a simple few body problem, and you don't need to deal with kind of a lot of external complications. That's in fact how we think about particle collisions at the Large Hadron Collider. However, if your dark matter particle is bumping into a detector full of stuff, well, the ground state of your detector is not the vacuum. It's got a bunch of interacting electrons and nuclei that are all kind of doing their thing. They can be in very interesting exotic states. And so really, it's kind of more like what happens if you throw, maybe it's a bit of a tortured analogy, if you throw a billiard ball into this ball pit, kind of a bunch of stuff is going to go kind of moving around. All these things are colliding with one another. And there really isn't a sense you can talk about an interaction between dark matter and a single constituent of this target. So when does this picture on the left hold versus the picture on the right? Well, it depends on the energy and momentum scales in your system. So knowing the dark matter velocity tells us that in units of its, in natural units, its momentum is about 1,000th of its mass, and its energy, so 1/2 mv squared, is down by another factor of 1,000. So if your dark matter has mass of 1 GeV, carries typical momentum of 1 MeV, and typical energy of 1 KeV. So your detector can be thought of as a bag of free particles if E chi and P chi, the dark matter energy and momentum, are the largest scales in your system. As you start dialing down the dark matter mass, that assumption starts to fail more and more. So if your dark matter has mass 10 MeV, its kinetic energy is comparable to atomic binding energies. So you really have to care about the bound states of the electrons in an atom. Another order of mass down, you run into things like the band gap of semiconductors. Another order of magnitude, you run into phonon energy, so the energies of quantized lattice vibrations in solids. And for really, really light dark matter whose mass is much less than an EV, you can think of the dark matter actually as a macroscopically coherent field that has more wave-like behavior than particle-like behavior. So I'll get to this at the end of the talk. But this is telling you that if your dark matter is lighter than a GeV, condensed matter physics really is mandatory. It's not optional. You need to consider this coincidence of scales, all of the interactions in your detector that are happening kind of on these energy scales. Okay, so with that introduction out of the way, let's focus first on this mass range between about a KeV and a GeV that I'll just call sub-GeV dark matter or sub-GeV particle-like dark matter, where if you can calculate the phase space occupation, so the number density times the cube of the de Broglie wavelength, you find that's much less than 1. So dark matter particles are sparse in phase space, and collisions with particles are rare events. The kinetic energy carried by the dark matter, again, is 1/2 mv squared. So the kinetic energy is a KeV at the upper range here, all the way down to a millieV down for dark matter masses of a KeV. So those are very, very small scales. And so you need to start looking for kind of exotic condensed matter systems that have those excitation energies, of which I'll discuss a few as we go. Okay. So because we're not thinking of our detector target as a bunch of free particles, the most useful formalism to use is one of what's called response functions. So let's just imagine that I've got some detector target symbolized here by this generic rubber ducky cartoon. You can insert your favorite detector here, liquid nobles, or a solid state detector, or something else. So dark matter comes in with momentum m chi v. It deposits momentum q in the target. And the energy lost by the dark matter you just get by comparing the kinetic energy before and after the collision. So there's a relationship between the momentum deposited and the energy deposited given by this. So note that I'm not writing down the state of the detector as if it were just a free nucleus at rest, because there might be some very, very complicated many body states in here, which may or may not be momentum eigenstates. There's really no sense of momentum conservation here yet at all. Instead, you want to ask the question, if I poke the target with momentum q, is there some energy eigenstate at the energy omega q corresponding to that momentum transfer q? And the object that controls that behavior is called the dynamic structure factor. It's one example of a response function. So it says you take the collision operator e to the iq dot r, where r is a position of the stuff in your target that dark matter is interacting with, could be electrons or nuclei. You sum over all of the many body final states in the target, you square this matrix element, and you weight by a delta function at energies of these final states omega f that only clicks if you equal this omega q that is the energy deposited by the dark matter. So then the total rate you would get is integrating this dynamic structure factor over all possible momentum transfers, that's the quantum mechanical part, times maybe some form factor describing whether dark matter interacts through a long range or short range force, so a light or a heavy mediator particle, and then integrating against the dark matter velocity distribution, because there's some spread in the possible dark matter velocities that you have to account for. So in the red are dark matter properties, in the blue are material properties, and this equation holds for any many body system, as long as you can compute this object S. So this equation actually tells us something interesting about what happens on the time scale of a day. So it turns out this dark matter velocity distribution in the frame of the Earth is not actually constant in time, but it rotates on the period of a sidereal day. So as the Earth is rotating, its orientation with respect to the wind of dark matter, which is kind of coming at us as the sun traverses an orbit around our galaxy, this dark matter velocity distribution rotates over the sidereal day. And therefore, if your dynamic structure factor is peaked at particular directions of the momentum transfer, then this rate is going to change periodically because this omega q is coupling together the momentum and the dark matter velocity. So as the direction of the dark matter velocity rotates in the lab frame, you can get a signal that has a characteristic oscillation on a period of actually 23.97 hours is a sidereal day, which is the day with reference to the kind of a fixed frame of the galaxy. And this really is a smoking gun for a dark matter signal, especially if you have a background that doesn't modulate over the course of a day. And many backgrounds that one encounters in low threshold physics might oscillate over the period of a year, but very few of them are going to oscillate over these 24 hours. So if you see this modulation in the rate, this really is a smoking gun for a dark matter signal. And a detector material that permits you to see such a modulation will be really great for being able to claim a discovery. So most of the condensed matter systems I'll talk about in this talk fall into that category. Okay, so let's look a little bit at the kinematics of sub-GeV dark matter. So if I strip off the velocity integral, then the rate for a fixed velocity is proportional to this integral over this dynamic structure factor. And if I look at the equation for relating omega and q, and I saturate that dot product, that tells you the energy deposited is bounded by this inverted parabola. So for a dark matter mass of 100 MeV and a velocity of 10 to the minus 3 times the speed of light, dark matter scattering lives inside this inverted parabola. And the goal basically is to find a material where this dynamic structure factor has large support inside this parabola, because that'll give you the largest rate. What's interesting about these particular scales here is it's kind of an underexplored energy momentum regime, because it's too high energy for things that are typically interesting for condensed matter physics, but it's too low energy for material science, where you're looking at things like radiation damage from passage of high energy particles through some material. So a lot of the things that I'll talk about are materials that are kind of known, where the response is known in certain regimes, but maybe not as precisely as you'd like in the regime relevant for dark matter, which is tied to the fact that we do know the dark matter velocity, even if we don't know its mass. Okay, so just to look a little bit more at the boundaries of this parabola. So the upper boundary corresponds to forward scattering, where the momentum transfer is as small as possible. The apex of the parabola is where you stop the dark matter. So imagine like a billiard ball collision, it stops, then your target gets all of the energy and momentum. And then this right-hand side is kind of like it hits a brick wall. So there's a large momentum transfer, but very little energy is deposited. Okay, so on that plot, I can now shade some regions corresponding to the dynamic structure factors for some kinds of systems. So atomic and molecular systems have excitation energies at the EV scale, and wave function supports on momentum transfers on the order of the inverse Bohr radius. So the EV scale is set by alpha squared times ME, which is the Rydberg constant. The momentum scale is set by alpha times ME, which is the inverse Bohr radius. And that happens to be just right for sub-GeV dark matter. Kind of these regions intersect these dark matter parabolas. Some of them require lower excitation energies depending on the dark matter mass, but everything has some support inside here. And so this was pointed out only a decade ago that atomic and molecular systems are really good for detecting sub-GeV dark matter. And there's been an absolute explosion in new proposals for experiments, and actually experiments that are currently running, taking advantage of this fact. That has led to some really exciting developments that I'll highlight for you here. So one system that I've been thinking about a lot recently are aromatic organic crystals. So let me just go through this for you. So I personally actually never took organic chemistry when I was in college. I now kind of regret that because I'm finding myself having to use translators who are versed in both chemistry and physics to understand the properties of these systems. Aromatic refers to molecules that are made up of carbon rings, and they tend to have a planar structure because carbon has two types of bonds. There are these sigma bonds that basically bond the carbon atoms to one another, and then there are these covalent pi bonds where there's orbitals that stick up out of the plane where the electrons are shared between neighboring carbon atoms and kind of delocalized across these entire rings. And those are the states that are responsible for the lowest energy electronic transitions. So the fact that this molecule lies in a plane gives you a violation of isotropy. So this system is not spherically symmetric. There's a plane and then there's a normal vector. And indeed, that is going to give you an anisotropic response that can lead to daily modulation. So what is the kind of signal one would see from such a detector? If dark matter scattered off of an electron and excited it to a higher state, as that electron de-excites, it emits some scintillation photons. And here's a movie showing what happens if you shine a UV pen light on a crystal of this T stilbene molecule. And you can see that a bunch of stuff comes right back out at you. So that's not like a reflection. And in fact, if you watch that movie again, you can see kind of shining at the table, you don't see much at all. And then it just lights up like crazy because indeed this molecule scintillates at wavelengths corresponding to kind of UV down to the blue or the violet that we can see. So if I now plot the response function of this molecule, sort of at a particular momentum slice, the hot spots tell you the size of the response function at a given momentum transfer in the plane of the molecule. And so you can see these characteristic peaks that are a characteristic momentum scale. And then these beams correspond to the kinematically allowed regions for dark matter that are like the three-dimensional generalizations of that inverted parabola I showed you on a couple slides ago. So over the course of a day, those beams traverse these different peaks of the response function. And that gives you this daily modulation where the rate is largest when you sit on top of the peaks and the rate is smallest when you don't. So the great thing about this is that, again, if this is a smoking gun signal for dark matter, you don't need a zero background detector. You can just take data for longer and longer and longer, and your statistical power will increase as the total number of events modulating more events at this time of day, less events at this time of day, it increases, and your background is just constant over that time. So there's an active collaboration now to build a prototype detector involving chemists at MIT, dark matter detector experts at Fermilab, and my group in Illinois. Okay, so thinking in more generality about this dynamic structure factor, the problem with trying to compute it from first principles is, well, how do you know what the correct wave functions are for the electrons? And when is it a good approximation to ignore the sum over all of the Avogadro's number of electrons in a given solid? So when is kind of this single particle picture a good approximation? So it was a decent approximation in these molecules that I showed you on the previous slide because they have relatively few electrons. But in a big condensed matter system where the electrons are delocalized over the whole sample, it's not always clear when this is a good approximation. And because electrons are light, they do all kinds of crazy things in condensed matter systems. So at low temperatures, they can pair up into Cooper pairs and give you a superconductor that has really interesting properties, like you can levitate this this cube of stuff through diamagnetism. You can have materials where the electrons act as if they're massless, or materials where the electrons act as if they're much, much heavier than their mass in vacuum. So in general, it'd be good to have a way to understand this dynamic structure factor, even in materials where the electrons are behaving in all kinds of interesting ways. So it turns out there is such a way of measuring the response function. What you do is you fire an electron beam into your material and you watch at what angle it bounces out. So just like deep inelastic scattering was the way that we could first measure quantum chromodynamics of the structure of the proton using quantum electrodynamics, so the electromagnetic interaction of the electron with the quarks inside the proton. So electrons here can kind of act as a proxy for dark matter. When you fire them into the target, that's measuring the perturbation of the electron density at a given momentum transfer and energy transfer. And if you can measure that thing with an electron beam, then the function that you extract, which is related to the dielectric function in the case of dark matter that interacts with electrons, you can plug that into your rate equation and you can figure out what the scattering rate is going to be without needing to calculate this thing directly from first principles. There's a little bit of modeling involved, but this works really well for materials where the electrons have really interesting and complicated properties. And an amusing aspect to this story is that this idea of measuring the response of electrons in a solid using electron probes goes all the way back to this really nice paper from 1959, kind of rediscovering things that were known in the condensed matter literature and applying them to dark matter is a common theme in my research. Okay, so we started a collaboration to do these kinds of measurements for really exotic materials with very, very low band gaps. So here's an example of a material with a gap on the order of 10 millieV, 2 orders of magnitude smaller than the gap in silicon. It also has an anisotropic response. So we're going to measure the response function of this material using this electron scattering technique at Illinois. These materials are synthesized at Los Alamos. We're going to build some detectors to see the single electrons that are scattered with our colleagues at SLAC. And then there's a theory going on both in my group and the group at Los Alamos National Lab. So we're performing the first measurements on these kind of exotic materials now, and hopefully building a prototype amplifier to detect these electrons soon to try to get at this very, very low mass dark matter range where you really need these materials with rather exotic properties that have these small excitation energies. Okay, so one more interesting fact about the interaction between electrons in a condensed matter system, you never get a bag of free electrons. So you always have a system where your electrons are talking to some nuclei. They might only feel some periodic potential in a lattice, or they might be core electrons and be very, very strongly coupled. But regardless, quantum mechanics tells you that if you hit a nucleus in a state where you have electrons coupled to the nucleus through the Coulomb interaction, then you can get electronic transitions, even if your dark matter basically doesn't see the electron and only sees the nucleus itself. So this goes by the name of the Migdal effect. And it was first proposed way back in the 1930s, related to things like the change in nuclear charge in alpha and beta decay. But in atoms, semiconductors, and recently by my group in molecules, we've worked out the formalism of this effect. And the reason you might want to do this is that electronic excitation energies are typically much larger than nuclear recoil energies. So even if dark matter hits the nucleus only recoils with a tiny amount of energy below the threshold of your detector. If you can see electron excitations, you can still see the signature of this event sort of indirectly by the electron excitation, even if you can't see the nucleus. So you can avoid your threshold. But this is an effect which is actually usually ignored in condensed matter physics because it's parametrically small. It goes like the ratio of the electron mass to the nuclear mass, squared sometimes, so which is on the order of 10 to the minus 5. So the probability of this happening is very, very small. However, if your detector threshold means that if this didn't happen, it would be totally invisible, a small non-zero rate is definitely better than a zero rate, so it's worth looking at. So I'll just describe to you an interesting way that this manifests in molecular systems. So taking a diatomic molecule is a simple toy example where there's just 2 nuclei separated by some vector rho. Let's imagine that somehow I managed to fix the orientation of all these molecules. Then the matrix element for dark matter nuclear scattering is going to involve nuclear states. It's going to involve an operator like this. And modeling these nuclear states as a vibrating harmonic oscillator, you can find that the squared matrix element has this typical form, where it depends on the dot product of the direction of Q and the direction of the molecular axis. And this object in here is kind of controlling the size of this exponential, depends on the nuclear mass, a typical vibration energy, and the momentum deposit. And it just so happens that that number is order 1 for dark matter of mass of 100 MeV. So once again, nature has been kind to us and has given us a coincidence of scales where we can probe sub-GeV dark matter with, in this case, a diatomic molecule. So looking at what the rate is for electronic excitation in carbon monoxide, which is just a toy example. So the daily modulation of the rate, you see again these characteristic curves that kind of dip at this time and rise again. But you see this really interesting crossover where actually the phase of the modulation flips. You now get a maximum midday instead of a minimum as dark matter gets heavier and heavier, which is right around when this exponential factor starts to turn on. So this is great because it means that not only do you see a large modulation, but the phase of the modulation depends on the dark matter mass. So if you see the signal, you can basically measure the dark matter mass. And kilogram for kilogram, what this plot is showing you is compared to the Migdal effect in solid state systems like silicon. So you should compare our purple curve here with the red curve for silicon. Kilogram for kilogram, you get approximately the same rate. So you don't really sacrifice anything, and what you gain is this very distinctive daily modulation signal. That said, getting a kilogram of carbon monoxide is just ridiculous. That's never actually going to happen. What we want is to calculate the same effect in, for example, these organic molecules that I showed you on the previous slide, because then you can get two things for the price of one. You can probe dark matter electron scattering and dark matter nuclear scattering at the same time. However, the two-body problem was already hard enough. The system with 14 nuclei and a whole bunch of electrons is much more complicated. We're leaving that to future work, but we're working with some material science theorists to try to understand how we compute these interesting nuclear matrix elements in these larger systems, and hopefully understanding how this Migdal effect is also going to work for realistic molecular systems that we can actually build a detector out of. Okay, so on the next slide, I'm going to switch gears to talk about much lighter dark matter. So maybe now's a good time to pause for questions if anybody in the audience has any.
Hi, thanks for taking a break. I wanted to just get a sense of the scale of the detectors that you're thinking of, and you know how you minimize background for these kind of detectors.
Right. So the kind of standard benchmark that everybody talks about is a kilogram year of exposure. So kilogram detector taking data for a year. That's the eventual goal of such things. But like, so for example, for this, let's see, how do I go backwards? Sorry. Let me just back up my slides for 1 second so I can let me share this with you again. Okay, so I'll go back to the regular screen view in a second, but I just want to show you this crystal already has a mass of a few grams. So you can get single crystals of this transstilbene already, and then you might be worried about backgrounds like, say, carbon-14 decay. So those are certainly an issue. However, it's actually really easy, relatively speaking, to purify these organic molecules, because basically you can make them as liquids. You can kind of precipitate out the heavier stuff and then get them to solidify without the carbon-14. There kind of isn't a lot of place for radioactive things like uranium to kind of sit interstitially. There's kind of no place in the lattice for them to sit, and you can also kind of precipitate those things out. So we're not exactly sure what all the backgrounds are going to be. But again, many of these backgrounds are sort of very high energy things that have a tiny low energy tail. And so for these relatively small detector masses, those backgrounds aren't expected to be kind of a severe impediment to seeing a signal. What we've calculated for this material is assuming, say, a background rate of like 1 per minute, you could still probe really interesting parameter space in a year. But obviously it remains to be seen. You actually have to go and build the prototype and then see what happens.
Thank you.
Hi, so we have a similar question actually from the Q&A asking for these detection schemes, it would be difficult to understand the systematics and how you discriminate error from signal.
Right.
Yeah, so do you want to maybe go into a little more detail about the systematics and how to get a handle on them?
Sure. So I think the best handle that we have is these daily modulation curves. So let me share my screen again. I'm not an experimentalist, but talking to many experimentalists, it is very hard to come up with a background that's going to look like this, that has kind of order one variation over the course of a day at energies on the EV scale. So materials that exhibit daily modulation are going to be really helpful for distinguishing a signal from background. At this point, not having actually operated a prototype detector out of any of these materials yet, that's kind of the best I can say. But that's why we started by looking for materials that already have this anisotropy that would allow us to sort of have this systematic handle.
Okay, I think that's it for now.
Great. Okay, so let me go on, and then I'll take questions at the end of the talk also, of course. Okay, so going back to kind of this 50 orders of magnitude plot, let's now zoom way down at the low end and look at dark matter that's lighter than an EV. So in this case, actually, its phase-space occupancy is much larger than 1. So already that tells you it has to be a boson, because you just can't pack more than 1 fermion in each cell of phase space. The kinetic energy carried by an individual dark matter particle is unobservably small. However, that doesn't stop us in the case of photons from seeing microwaves. In fact, that's how all of our cell phones work. The individual kinetic energy carried by a microwave photon is of order micro EV. However, the fact that you have many, many of them acting together lets you detect something macroscopic. And so in this regime, you can kind of think of dark matter as wave-like. It's behaving like a classical field. And this really is a new paradigm for dark matter detection, where there's been tons of progress also in the last 20 years, because it's so different than kind of the particle-like rare event scattering that we've been focusing on in the earlier part of this talk. So just a brief refresher on how wave-like dark matter looks. So it's this oscillating field where the amplitude now is set by the local dark matter density, and the oscillation frequency is set by the dark matter mass. And then there are small spatial gradients that correspond to dark matter velocities. So the fractional gradient compared to the time derivative is on the order of the dark matter velocity. And the fact that the dark matter velocity is small means that it takes a long time and a long distance for this wave to get out of phase of itself. So you're drawing these velocities from some distribution that has some spread, which is of order the typical speed. And so you can think of the de Broglie wavelength of this field as the Compton wavelength enhanced by a factor of 1 over v, which is about 10 to the 3, and then enhanced in the temporal component, because this thing goes like 1/2 mv squared. So the coherence time is of order the oscillation time times a factor of 1,000,000. So if your dark matter had mass of 10 to the minus 9 eV, it's like a field that is coherent over a kilometer and over a time scale of a microsecond. The Compton wavelength is a kilometer. The oscillation time is a microsecond, but this is telling you that actually it's coherent over 1,000 kilometers and coherent over an entire second in a detector. So what you're actually using is a small velocity of dark matter to help you instead of hurt. So for particle-like dark matter, small velocity was bad because it meant not very much kinetic energy. Here, small velocity is good because the velocity of dispersion is also small. Therefore, this field stays coherent for a long time. And just to justify my statement about classical physics being fine, so for that dark matter mass, the total number of dark matter particles that make up this wave is about 10 to the 18 per cubic centimeter. So really seeing a change in one dark matter particle is basically unobservable. So kind of the quantumness of this classical field in most regimes doesn't really play a role. Okay, so what should we measure? So I'm calling this field A because a canonical example of this ultralight dark matter is the so-called axion, which has certain couplings to electromagnetic fields and also matter. So it turns out that what you get in a background of this dark matter field is that static things turn into oscillating things. So if you put in a static magnetic field, what you get out is an oscillating magnetic field. If you have a bunch of spins that are all oriented along some direction, they can couple to the dark matter gradient, and it looks, for all intents and purposes, like this is an effective oscillating magnetic field. So this is an example of something where you can borrow a lot of techniques from nuclear magnetic resonance, and that's what I'll get into for the remainder of the talk. You can also get a time-varying electric dipole moment for things like the neutron you can measure in similar ways. And so this particular coupling is what I'll focus on and is known as the axion wind, because the idea is that the gradient is proportional to the velocity. So it's like you have a wind of this dark matter wave that's kind of coming at you, coupling to nuclear spins in this particular way. Okay, so now I want to briefly switch gears and describe for you a really fascinating condensed matter system that was brought to my attention by one of my colleagues at Northwestern, who's been studying superfluid helium for his whole career. So superfluid helium-3, so helium-3 is a fermion, and so it can form a superfluid when these two fermion atoms pair up into Cooper pairs, forming a bosonic state that can then condense. There's a phase called the B phase that exists at a certain temperature and pressure that exhibits a very curious phenomenon, where if you apply a magnetic field in the transverse direction, so I have some magnetic field that's pointing up, it's got some gradient, so it varies slowly over this sample, and then I turn on some pulse in the transverse direction, what happens is the system separates into two phases, where in one of them, the spins are all relaxed along the magnetic field, and in the other one, they're all tipped at this magic angle of 104 degrees. That seems like a kind of a random angle, but ends up basically being predicted based on dipole-dipole interactions in these helium atoms. And then what happens is this entire macroscopic part of your sample is going to process together, so the spins are going to rotate together in phase at a Larmor frequency. So gamma is the gyromagnetic ratio, B is the magnetic field, but it processes at the local frequency corresponding to whatever the size of the magnetic field is at the boundary between these two domains. So as losses in the system cause you to lose some angular momentum to make, like scattering in the walls, for example, this domain boundary drifts up, the precession frequency correspondingly drifts down, because now this boundary is sitting at a region of slightly smaller B field. So what you see, if you look at the nuclear magnetic resonance signal, you put some magnetic field detector kind of on the outside, and you look at some flux through a pickup loop, you see this frequency gradually drift down. And what's really neat about this system is that it naturally scans over frequencies. So again, the problem with dark matter is we don't know its mass. So we don't know at what frequency it's oscillating at. You'd like it to resonate. You'd like this resonance condition to obtain, but you don't know what resonant frequency to use. So having a system that naturally scans over frequencies for you is great for covering as much dark matter parameter space as you can. Okay, so this is called the homogeneous precession domain, or HPD. So what is dark matter going to do? So again, dark matter interacts like a magnetic field. If some component is along this transverse direction, it's going to exert a tiny force on this domain wall, either kind of nudging it up or nudging it down, compared to how it would like to relax in the absence of this dark matter field. And so we did some numerical simulations, and your signal is a tiny, tiny frequency shift. So here you see this drift of the frequency kind of down, and then at some time scale where you get into resonance with whatever the dark matter mass is, the frequency kind of either bumps up or bumps down and stays like that as the system continues to evolve. So once again, this is a system where you can look for a daily modulation signal, because you can set your magnetic field's gradient to whatever you want. You can take many measurements over the course of a day, scanning the same dark matter masses at different times of day, where you expect the size of the signal to be different. And again, we expect that to be able to help with systematics. That's a subject of ongoing work right now. So just to close on this, so what is the sensitivity you might expect? So now the parameter space is dark matter mass on the x-axis, dark matter nucleon coupling on the y-axis. There's a orange band or a yellow band down here that corresponds to kind of a preferred parameter space where dark matter is solving the so-called strong CP problem. So these black, red, and blue curves show you the sensitivity you might expect for various experimental parameters, data taking time, relaxation time of the system, volume, that kind of thing. But the fractional frequency shift you'd expect kind of on this red curve is on the order of 10 to the minus 14. So really now we're in the domain of needing things like quantum information and quantum metrology, coupling your system to an atomic clock to make sure you have a really good frequency reference, that kind of thing. And what's being compared here is this red dash curve. That's another proposal for detecting the so-called axion wind. which is using essentially classical NMR. So you can have some system like hyperpolarized xenon where you can get all of your spins basically pointing in the same direction, but you don't have this macroscopic domain that's processing coherently. It's easier for the spins to get out of phase with one another, and they only process at one frequency. So it requires a very fine tuning of your external magnetic field, which is a feature that actually this HPD setup nicely avoids. So there's an active collaboration with experimentalists at Northwestern trying to build, they actually have the superfluid helium sample, but trying to set up this HPD and see how long you can get the coherence time and set up the B field gradient to be just right for this mass range of axions. So I'll ask you to stay tuned for that. And apologies, that's hopefully the only pun in the talk. Okay, so let me just close by telling you that the future for light dark matter is very bright. So here are some kind of motivational plots from a recent SNOMAS white paper. So SNOMAS is the decadal planning process in high energy physics meant to motivate kind of the next generation of experiments and get funding agencies to understand these are really fun things to look at. So the current exclusion regions where we haven't seen anything yet are shown in tan, but there are some key milestones in orange that we expect near-term experiments to be able to cover. There are farther-term experiments, among which I've discussed several in this talk, where we can get at more of this kind of really interesting parameter space. And what I hope you're going to take away from this talk is that detectors are uncovering new parameter space every day. Hopefully, we'll get some of these prototypes operating soon. But we really need the tools and techniques of condensed matter physics to determine the true sensitivity and hopefully uncover a dark matter signal. So with that, let me say thanks for your attention and highlight the really fantastic work of members of my group. In particular, Ian Harris, who's a third-year grad student who worked on the Migdal effect project, and Christina Gao and Jan Schut-Engel, who are postdocs who work on the Superfluid helium project. So thanks very much, and I'm happy to take questions in the remaining time.